Hi folks, it's Mr. Moodledge here again with another video. This time we're looking at lesson number 1, Introduction to Functions and Relations. So, important thing to note here is that a relation is it's defined as a set of pairs of input and output values. What I mean by input is x values, output values are referring to y. So if you think of like a table of values, right? Let's say this is the relation, the graph of the relation I'm looking at, y equals x plus 3. I want you to think of this x as being an input. So when I give an input value of 0, well, 0 plus 3, the output is going to be y. This input-output thinking is very helpful for dealing with functions and relations, as you'll see. So when the input is 1, the output is 4, according to this, because 1 plus 3 is 4. Likewise, when it's 2, 2 plus 3, the output then becomes 5. So that's that. Here we have another relation, an example of a relation, y equals x squared. Now, let's say we're looking at, so we have our relationship, so our equation right here, x is equal to y squared. Let's say I have an input value of 9. What is my output? Well, I have to take the inverse of the square, so square root it, the opposite. And when I introduce, and that's what this note is saying right here, notice that I had y squared. When I'm getting y on its own, I have to introduce the square root, the radical, so I have to put plus minus. In other words, referring to this diagram, what I've just said is for an x value of, let's say, 9, which in this diagram it doesn't really show because it's off the x-axis, but let's say for an x value of 4, well, I'm going to have two y values, positive 2 and negative 2. For an x value of 1, let's say, I'm going to have positive 1 and negative 1, right? So two y values, and that's the reason why I have to put the plus minus when I take the square root. So here's another example. This is the equation of a circle centered at 0 with a radius of 3. It looks like this: y equals x squared plus y squared is equal to r squared, where r is the radius. And now I can see from here that for this given graph, the radius is 3. So hence I have this equation here. That's a relation. Good. All right. So with that in mind, now we're able to take a look at a different type of relation, which is an ordered pair. It's just a list of coordinates right here, as we could see. It's just a bunch of points on a graph. Okay, so this is another type of relationship right there. Cool. We also briefly looked at modeling relations. So let's say we have a scenario where someone named Bob has a summer job cutting lawns for $10 an hour. What are different ways we can model this mathematically, this relationship? Well, I always can fall back to my table of values where I'm looking at time and pay, right? When he works 0 hours, he's earning 0. If he works 1 hour, he's earning $10 and so on and so forth, right? I also have a graph, right? Can represent the x values of the input on the x-axis, the independent variable, and the dependent variable on the y-axis, the output, right? So the more hours he works, we can see it's a linear trend here, a linear relationship. His pay goes up as well. Linking those two is probably one of the most powerful forms of modeling mathematical relationships, which is an equation. So P is equal to 10t. Some things that might not be that we might not use every day are ordered pairs. These are very nice for discrete relationships, so individual points. So when he, like input output, right, x and y, so 0 hours, $0, 1 hour, $10, 2 hours, $20, and so on and so forth, right? The final one here, which is new for us perhaps, is mapping diagram. So this is kind of like, I like to think of it like two clouds. That was a good analogy. So this first cloud is like our x values, and the second cloud is our y values. So we see here when x is 0, it maps to an output of 0. When an input is 1, it maps to an output of 10. That's the reason why it's called a mapping diagram. When we take a look at which models are generally preferred, if we're not given an equation, then by far, like the equation, personally, I think it's one of the best models. But, we can also say that table of values and graphs are also good, very good models for representing any type of relation in general. Okay. Okay, now we get to defining what a function is. So a function, what you need to know is it's a very specific type of relation. So if we take a look at a relation as a big picture, a function is a specific class or a subset of that larger set, right? A function, what it is it's a relation where every input x has exactly one and only one output. So here is like, we were talking about function machines, or a relation like a machine in terms of what's going on. Functions are more predictable. So you can put in a single thing and calculate precisely what comes out. So we were talking about a vending machine, and let's say you press on the button A1. Well, you expect, the machine to work and then feed you chips, let's say. But that button is specifically tied to chips, right? In math terms, if I feed the number x equals 1, something is going here. There's like a system there, an equation or something. There's a process going on, but that'll give me an output maybe of 3, let's say, right? So input, output. Every input corresponds to just one output. Now, a relation is more broad. However, with that, sense of broadness comes the unpredictability. So it's like you put something in and you never know precisely what you're going to get out, right? Because there's more than one thing that can come out. So if I press the button here, maybe this vending machine's broken, or there's some like deal going on with the vending machine. Maybe there's a promotion or sale. I press the button A1, and now instead of just giving me chips, well, maybe sometimes I get chips. Maybe sometimes I get a drink by accident. Maybe sometimes I get nothing. Maybe sometimes I get chips and a drink. So it's very random in that sense, or not random, but it's less easy to be. It's less predictable. So here's an example in terms of numbers. If I plug in x equals 1, maybe into some system, maybe I'll get y equals 3 and y equals negative 3. So it's a little bit unpredictable like that. I have more than one output for a single input. So of note here is this interesting property. All functions are relations. Yes, that's true, because all functions are types of relations. Relations, the bigger category, but not all relations are functions. True. I can't say all relations are functions. And when we look at these graphs, I ask myself, okay, what are these? Which ones of these are functions? Well, that's where we talked about the vertical line test, and that's what's coming next. Graphically, it's one of the best tools. We literally draw a vertical line as if it were like passing through each segment from left to right of this graph. And as long as that vertical line just touches the graph, the equation, the line at one point, then it is considered a function. So this cross is that's okay. Here, it would be like at this vertical line, okay, sure, it would just touch that one point. But once we get to like somewhere like here, well, there it touches the curve, the relation here, it touches that graph twice, so it wouldn't be a function. Same thing here. So there are points that touch more. So every input of, let's say, x equals 2, well, I'm having two outputs. I'm having an output of like positive 1.5 and negative 1.5. So it's kind of ambiguous like that. This is also an example of not a function, because I can have, a vertical line like this, and it touches that twice, right? Vertical line like this, it's touching it twice. A value of x equals 2, an input of x equals 2, is having an output of positive and negative numbers right there, close to, I guess that's almost like 2, positive 2 and negative 2. Okay, so that's the graphic test for determining if something is a function or not. It's called the vertical line test. Okay, the algebraic test, if you have an equation and you don't have a graph, is you could just sub in values for x and see if there is, as long as every value of x satisfies a unique value of y, you're okay. The moment you see that a single value of x gives two values of y, then it's not a function. Right. So that being said, like it's just the same thing as the vertical line test in using numbers, subbing and getting that. So here are some examples. Which of these following are functions? Again, I just used the vertical line test. So you can see the vertical lines would just cut the graph at one point. So this is a function. Here, as long as it cuts it more than once, it's not a function. So here, even though there's squiggles here, it's only cutting, like if I draw a random vertical line here, it's only cutting it once here. Here, it's only once. So everywhere like that, as I move left to right, it's only cutting the graph at one point, touching the graph at one point. So it's a function. When I have something like this ordered pairs, it's very nice and helpful to draw a little sketch. So we could see if I sketch these points right here, so 1 and 3 right here, and then 2 and 4, we'd see it's kind of like, it's not a line, these are discrete points. But nevertheless, if I just draw lines through them vertically, I'm never going to cut more than 1 point. So that this is a function. This one right here is not a function because every, if I were to, again, draw the points on a graph right here, on a grid, I would see that they all share the same x value, and they have multiple outputs for that same x value. So it's literally a vertical, if I put a vertical line through that, well, all the points would go through that, so it's not a function. Here, this is on the other hand a little bit different. This is the same y value, but I have different x values. So 3, 1, 4, 1, 5, 1, 6, 1. I can go through the vertical line test here, and like at this point, it would only cut it once. At this line, it would only cut it once, and so on. So it's a function. That's okay. This is also a function because, as we saw earlier, it passes the vertical line test. This is a circle. Well, there's 2 points that touch it at that vertical line, so it's not a function, right? The radius here would be 5. Square root of 25 is 5. Okay. Which brings up the question, when we were looking at G here, are all lines functions? Well, it turns out no, not all vertical lines are functions. The question here was no, not vertical lines are not functions, they're relations, because by definition, if I drew a vertical line on top of that, well, every point on that line would be touching that vertical line. So it's not a function, right? Like you can imagine a value of x equals 2. Well, I have infinite outputs for that single input, so it's not good. Okay. Now we're going to take a little bit of a different direction here, and we're going to look at how can I describe or add constraints and describe how my function looks, and especially when I talk about boundaries. Where does it begin? Where does it end? Kind of giving the scope of it's called the domain and range. We're going to see what those mean in a second. But this is called set notation. So the way that I write this is there are 2 parts to the set notation. So there is domain, which is all the possible x values that my relation can take, and the range, which is all the possible y values. Now here, if I take a look at my a sketch here, if I have here it's a function. If I have a function like this, well, the domain is just from here to here, all the x values that it can take. The range, let's say those are finite points, it ends there. So from here to here, yeah. And then the range is also like the range of the y values. So from here to here, that ceiling. Okay, all possible y values. So let's take a look at some examples. I could have something like this, where it's a linear line, a linear relationship or a linear function here. And what's interesting is notice that it's going to stretch on forever this way and this way. It's going to go on forever. So all the x values are element of real, and all the y's are element of real. And before going back to this, I have to explain what the set notation is right here. So set notation, there's 2 parts, domain and range. So that, if I'm talking about x, well, that's my input, my domain. If it's x, if it's y, it's range. Then I have this letter right here, which is element. It stands for element. So x is an element. And then I have to include my number system. So there I have the real number system. I could have integers. In fact, here I talk about some of them. There's natural numbers. It's represented by the number n. That's like the counting numbers, 1, 2, 3. Whole numbers are the natural numbers plus 0, 0, 1, 2, 3. Integers are it's like natural numbers, 0, and then their opposites as well. So the negatives of those natural numbers as well. So here, since they go on forever, both horizontally and vertically, my domain is just x element r, real number, and then y element r in that case. But going back to the set notation here, once I give the number system, I have to incorporate this line right here. I mean, not have to, but if there are a condition, then this right here means such that. So let me write that down right here. Such that, that's what that means. That line right there, such that, and then here I write the condition. So x greater or equal to 3. This is an example of a set notation, and I cover that with the curly brackets right there, the braces. Okay, so let's take a look at this in context. So right here, like I said, this one is simple. It's just x element r, y element r. There's no restriction in x or y. Here, the domain is going to be x element real numbers such that x has to be larger or equal to 0, because I can't have negative x values, right? Does not exist. But y can go forever, like it'll increase both up and down. So y is just element r. Here it's a circle, so notice it's a line here, so I have to include all the points in between. Hence, it's a real number for both the in the domain and range, and such that the x's go from -2, so that's a -2x value, that's a -1x value, that's a -2x value, a -1x value, a 0x value, right? So on and so forth, all the way to from -3 to 3, because it's all that curve is covered there and the bottom one. So x is between -3 and 3. So x is larger than or equal to -3 and smaller than or equal to 3. And then I get for y, it's also an element of real numbers because it's, again, it's like the opposite of x. Right here, it's a nice circle, and it's between -3 and 3. Right? Y is smaller than or equal to 3, but larger than or equal to -3. So that works. Here, it's like a parabola. X, they go on forever, element real numbers. Y is also, sorry, I'm looking at the wrong one. Y in this case, so X is element real numbers. Y here is an element of the real numbers such that it's greater than or equal to -2, because it goes upwards from there. In other words, Y cannot be a number that's less than -2. Okay, here we have an oval shape, so not really a circle. So I have to go from -4 to 4 in the x, and it's an element of the real numbers. And then for the y, I have to go from, it's not a nice circle, so this would be -2.5 to 2.5, -2.5 to 2.5. Okay, and it can equal those values too. This is my domain, this is my range. Here we talked about for the first time what an asymptote is. It's like kind of like, you can think of it like a fence where my graph is trying to reach that or cross it or touch it, but it's actually not. It's getting closer and closer. So here for my domain, I just say that x is an element of the real numbers because it seems like they're hitting all these continuous points. And it continues this way, but such that x has to be greater than 0, not equal to 0 because it's never touching that line, but greater than that. Y, on the other hand, is just an element of the real numbers because there's no fence here or anything. It will keep increasing and keep decreasing this way. Okay, here I have a bunch of discrete points. So unlike what we've seen before, it's not continuous. So the way I go about this is, I'm just trying to see if I did this here. Does not look like I've done that. That's okay. Yeah, so I will say, yeah, no, it looks like I didn't, let's do it together. That's okay. So I will say here, I have x is an element of, there's two ways I can go about this actually. I think I did it over here. Nope, no, it's okay. It's okay. We'll do it together. Okay, so that's good. So this right here could be x is an element of the integer set because these are discrete numbers, like we could see here. So it's not like continuous, like a line, no line connecting them. So I'd say x is an element of the integers, and integers represented by the letter z, such that here I would say x is between, it seems like there's every x value, there's an x value at -1, -2, -1, 0, 1, 2, and 3. So then I'll say it's just all the x values that are integers between -2 and 3. So that's how I could say that for the domain. For the range, I would say y is an element of the integer number set, number system, and y is between -1 and +3. Okay, so that's how I'd go about that. Another way I could have said this if I really wanted, so that's option 1. This is perfectly fine for both domain and range. I could also just list my domain and range like this. I could have said x is equal to, because they're points, right? I can define them like -2, -1, 0, 1, 2, 3. might seem a little bit longer. And then for the domain, I could just say y, because I don't have to say it's part of the integer number set, because clearly these are integers, right? And then if I list them out this way, for y, I could say it's, well, it's -1, 0, 1, 2, and 3 for y. Okay, so that would work perfectly fine as well. Both of these are, both work. Both work. Okay, so you could pick any one you like there. Okay, sometimes this is more convenient because you're writing less, but this sometimes is easier to see, so both are acceptable. Okay, cool. We defined what domain and range were. Now that's good. Now we could take a look at these pictures, or these ones down here. These, ordered pairs of points. Just seeing if there's anything else here located. Yeah, describe where. Okay, yeah, we did that. Okay, so example 4. Here I have a set of ordered pairs, and like we did before here, I could list them out. Oh, so this is the one we did. I was looking for a different question. Yes. So here we could see x is equal to 1 in each one. So I could just say x equals 1. And then I could say what the range is. I could just say, well, it's 3, 4, 5, and 6. 3, 4, 5, and 6. That's one option. Or what I can do equally as well, same thing for the domain, or sorry, for the range, I could say y is an element of the integers such that y is between 3 and 6. Okay. For the domain, it would just make sense to just put y is equal to 1, x is equal to 1 for the domain, because there is no other x value. Okay. Here's an example of a square root where it's been given to us already. So y is equal to square root of x. So that's assuming it's the positive square root there. And so here I would say, well, x is an element of the real numbers, because I can find decimals here as well. I could put in decimals for x. And x, well, the smallest value of x that would make sense to be able to find a square root in order to do square roots is 0. And it could be 0. I could find the square root of 0. It's just 0. And so x has to be greater than or equal to 0. In other words, I can't find square roots of negative numbers for all intents and purposes of this course, right? We're not getting into imaginary numbers here. That's that. And then for y, well, if I have a x value, the smallest x value is 0, if I plug that in here, square root of 0 is 0. And then you could see as you increase the x, the input, your output is also increasing. So y is also going to be greater or equal to 0, but still part of the real number system. This is now quadratic right here in vertex form. So just identifying the vertex here, remember vertex form looks like this, is hk, where h right here, if it's negative, you got to remember to switch the sign here. So my vertex for this given equation would be 4, -3. 4, -3. So then I could just draw a little sketch here, 4 in the x and 3 down right there. And then it's just a parabola opening upwards because the a value is 1. If I want to write the domain for this, well, I would just say x is an element of the real number system, and that would be it for the domain, because this graph goes forever left and right in the horizontal direction. And then for the range, there's a little catch, so I would say x element r, yes, such that, or sorry, y is an element of the real number system, such that y has to be greater or equal to -3. Because I can't have negative, like for example, I can't have there's no output there's no output that exists such that it's negative, right? Less than -3. So I'll never get an output less than -3, right? Okay, cool. Now there's one more just like this. Again, the vertex here, just noting this, vertex is equal to -1, 5. So if I was to draw a little sketch here, -1 would be here perhaps, and then 5 up would be up here. It's not drawn to scale, but you get the idea. And then it's opening down because it's negative here. So it would open like this roughly, okay? And we could see, yes, not only is this a function, but the domain, similar to before, is an element of the real numbers, because it goes on forever this way and this way, like both ways, x left and right. And then the range, So y is an element of the real numbers such that y has to be smaller or equal to 5. So that's how that works. Okay. Cool. All right, we're good to move on now to the last piece of this introduction to functions, which is the mapping diagram. So here we could see the mapping diagram is okay. We're good here. Yes, we can see here the mapping diagram. Let me just change the color. So yeah, a mapping diagram is used when we have a set of ordered pairs. So essentially it's like two clouds. The one on the left is the domain, so the x values, the one on the right is the range. And then we kind of just draw arrows to show what values it maps to. What values of input does it map to in the output, right? So here we have an example. We want to see if this relation is a function or not, each one. So whenever, remember the definition of a function, when every x value corresponds to a singular y value, it's a function. So this 1 corresponds to -5, good. This stemming out from this input of 2 is a singular output. Stemming out of this input of 3 is an output of -5. Like, that's okay. Even though there's one output for different inputs, that's okay. The problem occurs when there's more than one output for a given input. So this actually turns out is a function, right? That is okay. Like, for example, the domain, for example, could be something like, e.g., time of day. Time of day. So let's say this is like, I don't know, 1 p.m., 2 p.m., and so on, like time of day. This could be like the temperature at night, or not night, but the temperature at that time, right? 1 p.m. Precisely. So it's okay. Like at a time of 1 p.m., we could have a temperature of -5. At a time of 3, we could have a temperature of -5 again. That's okay. It's just that we can't have a single time of day have two temperatures. That would not be a function when it's stemming out. So otherwise it's good. So this is a function. And then the range could, like I said, be temperature. Okay, good. Here I have something where it's a little bit different. It's, I have, for a given x value, it looks like I can have two y values. So immediately this is not a function, not a function. Right? In fact, if you were to like draw a sketch of this, right, in terms of like a grid, if you were to sketch these points out, you'd find that an x value of 2, well, you would have both 1 and 2 y values. So this right here would not pass the vertical line test, hence it's not a function. Okay, last thing I want to do here is go over what a mapping diagram, like more practically, what it looks like in context, like drawing one. So here it's saying draw a mapping diagram for y equals 5 with a domain of this. So I'm going to draw two clouds. So 1 and 2. This one right here is going to be my domain. So the one on the left is my x, and this one's going to be my range. Now, I could see here that I only have a singular range, y equals 5. So that's 5. But I have a domain of 1, 2, 3, 4, 5, and 6. So 6 values of input. So 1, 2, 3, 4, 5, 6. And then I'm going to draw arrows to connect, right? The input of 1 maps to 5, and output 5. The input of 2 maps to an output 5. 3 maps to 5. 4 input out maps to 5 output, and so on and so forth. You could see, so there's multiple, there's multiple ways of getting 5, but it's okay. It makes sense. This would be like a horizontal line. So this is a function, right? Not a line, a horizontal relationship. So like, for example, let's say this is x and y. I would have like 1 and 5, 1 in the x and 5 in the y, 1 and 5. And then I'd also have like 2 and 5, maybe. Not drawn to scale again, but you could see the idea. And then this would pass that vertical line test. It would be fine, right? Because it's just a horizontal line like this. Okay, not a line, but discrete points, but still, it would be horizontal is the idea. And then lastly here, a draw mapping diagram for when x is equal to 3. Well, here I have my domain, And here I have my range. Make that a little bit bigger. Okay, and let me enter those numbers in. So when I have a input of 3, I can have an output of well, it says here 1, 2, 3, 4, 5, 6, and now I can connect these. So a single input of 3 can have like multiple outputs. So this is clearly not a function, but I still am able to draw a mapping diagram here. So this one would be, I'll list it here. This one would be a function. That's okay. This is good. This one would not be a function. Not a function. Okay, and then this is what the graph of that would look like. X, rough sketch. Y, we would have like at 3, we would have these points. So like 1, 2, 3, 4, 5, 6, and so on. So clearly this would fail, like a vertical line right there would fail. It wouldn't pass the vertical line test, hence it's not a function. Okay, that is the end of that clip, folks. Here's the homework from the Nelson Functions 11 textbook. Please go ahead and try that. All right. Thank you and have a great day.